So in the last lesson, we talked about the different types of decay processes that unstable nuclei can undergo. Next up, we're going to talk about the rate at which these substances decay. We're going to do so by using something known as half-life. So half-life refers to the rate at which a substance decays. So by definition, half-life is the time it takes, so this is a time, the time it takes for guess how much of it to react. It's called half-life. So the time it takes for 1/2 of a radioactive substance to decay. And so we can see in the book on page 946 a figure of a particular substance undergoing decay. And that substance is strontium-90. Strontium-90 has a half-life of 29.1 years. According to the nuclear equation there, this isotope undergoes beta decay. So every 29.1 years, half of the substance decays into something else, and that something else, of course, being yttrium-90. And so 29.1 years, you have half of whatever you started with. So we started with 16 milligrams or 16 micrograms, actually that is. After 29.1 years, you would have 8 micrograms. After another 29.1 years, you'd have 4 micrograms and on and on and on. And so each half-life, half of the substance has decayed and half remains undecayed. And half remains as the original, in this case, strontium-90, that will undergo radioactive decay. Now, it should be noted, I believe I mentioned this before, radioactive decay is a first order process. So as we can see, according to that graph, as the amount of strontium-90 changes, the rate at which it reacts does not change. And so this is a first order reaction. Because I misspoke a little bit, the rate at which it changes does change, but its half-life does not change. Its half-life is constant. Its half-life is independent of the amount. So though the rate at which it decay changes, so if we took, say, the instantaneous rates, we can use that graph there, tangent line on any point, we'd see that the rate at which it decays changes, but the half-life, that's what I meant to say before, sorry about that, the half-life does not change. Indicative of a first order reaction. So in any first order reaction, although the rate does depend on the concentration of the reactants, the half-life does not depend on the concentrations of the reactants, as we'll see in a bit. All right, so we have a couple key equations here, just like with any half-life calculations. So this applies both to chemical reactions and nuclear reactions. So we have natural log of, that's kind of a big T there, A naught over AT equals KT. So just our regular integrated rate equation for first order reaction. So AT is the amount of a substance, and that could be in grams, moles, concentration, number of atoms, all kinds of different things that we're given the amounts of, especially with nuclear reactions. So the amount of that substance after some elapsed time t. A naught is how much we started with. K is our rate constant. T is the elapsed time. Second equation, again, because this is a first order reaction, we can write the equation for half-life. Natural log of 2 over K, so 0.693 over K, where of course T to the 1/2 is our half-life, and K is the rate constant. So if you're ever asked about the half-life of a radioactive substance, all you would need is the rate constant for that reaction, and that can be used to give you the half-life. All right, let's take a look at an example, 26.4. I'll read this to you. It says the cobalt treatments used in medicine to arrest certain types of cancer rely on the ability of gamma rays to destroy cancerous tissues. Cobalt-60 decays with the emission of beta particles and gamma rays with a half-life of 5.27 years. So every 5.27 years, half of that substance has decayed to nickel 60 in this case, as we can see by the nuclear equation there. How much of an original 3.42 microgram sample of cobalt 60 remains after 30 years? Now, there's a couple different ways we can do this. In Chem 1, and I'm not sure that's going to work too well here, but in Chem 1, I gave you a couple equations. So one of them is this: if we take the elapsed time, the amount of time that a substance has been decaying for, and divide that by the half-life, which is a constant for a substance, that'll give us the number of half-lives, the number of times that substance has been halved. And we can use that here if we take, and this I'm going to represent with the letter N, the number of half-lives. We can take this equation here, 1/2 to the nth power, that's an N, times our, here, let's write it this way, our starting amount. That'll give us our ending amount. Now this works particularly well when you have an even number, or sorry, I shouldn't say an even number, a whole number of half-lives. So after one half-life, half of the original sample remains. After 2 half-lives, 1/4 of the original sample remains. 3 half-lives, 1/8 remains. 4 half-lives, 1/16, and so on. Each time, half of the last amount. And so when you don't have a number of, even number of, or a whole number of half-lives, then that means you're going to have to use logs to solve this, which is fine. You can use log base 10, or you can just use one of the, or the integrated rate equation that I just showed you. So speaking of integrated rate equation, so we're looking at this, and we are given the half-life, and we are given the starting amount. And so we don't have enough information to answer this question just yet. And so what we're going to do is we're going to take the equation for half-life to find the rate constant. And so take a look there. That's 0.693 over K equals the half-life, half-life being 5.27 years, and we get a rate constant of 0.131 per year. So remember, rate constants for a first-order reaction has units of per time. Half-life here is given in years, so our rate constant has units of per years. And then we can take that along with the original amounts. The original amount was 3.42 micrograms. Plug that into our integrated rate equation and solve for a t. How much is left after 5.27 years? And so what we end up with is 0.067 micrograms remains after 30 years. So half-life equation first to find the rate constant. Once we know the rate constant, we can plug that in here along with the time and the original amount, and we're solving for how much remains after a certain period of time. All right, go ahead and turn to page 966. Problem number 53. This time we're looking for a fraction. So you can find a decimal first, that might be easier, or a percent, and then convert that to a fraction. So go ahead and pause the video, set that up, and see what you get. So here's our setup, just like in the last problem. Use the half-life to find the rate constant, which is 0.024 per second. So we're given the elapsed time in seconds. So our rate constant is per seconds. And then I use that in our rate equation, integrated rate equation. So I put a 1 here. So we're looking for fraction. So I'm going to calculate a percent. So using it as a decimal. So I just put that as a 1 here, solving for AT, and we get 60% remains. And as a fraction, that would be 3/5. So it depends. The question asks, can ask for a number of different ways of expressing the answer. In this one, I wanted the fraction that remains. So you can always find a percent. And again, you could put 100 here if you wanted. and then you would get 60%, but I just decided to leave it as a decimal, and then I converted that to a fraction. I go ahead and take a look at 26.5 on page 949. This one's a little bit different. Let me read it to you and then kind of walk you through the process. So it says a piece of wood taken from a cave dwelling in New Mexico is found to have a carbon-14 activity, and this is per gram of carbon, of only 0.636 times that of wood cut today. So sometimes we're given the rate of decay as this term activity, or sometimes mentions about the number of disintegrations per unit time. So this is a rate of decay, and this is per gram. So estimate the age of the wood. Half-life of carbon-14 is 5,730 years. So just kind of like we did before, we use the equation for half-life to find the rate constant. In this case is 1.21 times 10 to the negative fourth per years. And then it says here, if you look at the solution, the present carbon-14 activity will represent with N. Disintegrations per unit time is 0.636 times the original activity, which we're going to write as N naught. So N equals 0.636 N naught. So we'll substitute those in our integrated rate equation, and we're going to solve for N naught. And we end up with, again, notice in the setup there, we got 1 over 0.636, and we end up with a time of 3.74 times 10 to the third years, or 3,740 years, and this is how old that object is. So you can read in your text about carbon dating, the use of carbon-14 to determine the age of once living organisms, and so that is known as carbon dating. All right, you got one like that to try. Page 966, number 57. Go ahead and pause, set that up. All right, so once again, here's our setup. So I didn't mention this last time, but I just rearranged the equation for half-life to find the rate constant. So I put the half-life on the bottom here. And so we get a rate constant of 1.21 times 10 to the negative fourth per years. And then take a look at the setup here. So I use the activity as my amount, kind of the rates at which that substance is decaying. So A naught is going to have a higher value than AT. Substance will decay at a higher rate initially than it will over time. And so if you're ever wondering where those numbers go, put them in like that. And this time we're solving for T, trying to find out how old this object is. And so we get 5,180 years. All right, number 61, yet again, a little bit different problem in terms of the information that we're given. So go ahead and pause, set this up, and see what you get. So here's our setup once again. So this time the information we're given is the percent of the substance that would decay, so 99.0% decays. So we don't want to plug in how much decays, but how much remains undecayed. So if 99.0 decays, then 1% remains undecayed. So our AT value is 1%. So once again, instead of using percentages, I just use decimals. So 1 over 0.01. So 0.01, that is 1%. As a decimal, I think that should probably be 0.010 maybe, depending on your sig figs there. And so we're solving for T once again, and so the time it would take for 99% of that substance to decay, where you'd be left with 1% of the original radioactive substance, would be 180 years. All right, yet another different problem, 26.6 on page 950. Let me read that to you. A sample of uranium ore is found to contain 4.64 milligrams of uranium-238 and 1.22 milligrams of lead-206. Estimate the age of the ore. Half-life of uranium-238 is 4.51 times 10 to the 9th years. So on this one, something to keep in mind is that the uranium will decay to ultimately forming lead-206. So this is one of the natural decay series. And so we're given the amount of lead that you end up with. What we need to figure out is how much uranium was converted into that lead. So lead and uranium have different masses, and so we need to use that mass ratio. Really, this is kind of a stoichiometry problem. If you have 1.2 milligrams of lead 206, how many milligrams of uranium 238 must have reacted to produce that much lead 206? So your book doesn't use mole ratios. It would be a 1-to-1 mole ratio, and so they just go straight to molar masses. And notice they're not using grams, they're using milligrams. So the mass ratio in grams and the mass ratio in milligrams is the same, and so it's easier just to use milligrams. So that 1.22 milligrams of lead 206 originally came from 1.41 milligrams of uranium 238. So obviously, uranium 238 having a greater mass, you'd have more uranium 238s that reacted than lead 206 that was produced. And so once again, we want to find out how much uranium we started with. So we took the how much we have after the elapsed time t, 4.64 milligrams, plus how much reacted to produce the lead 206, 1.41 milligrams, to get a total of 6.05 milligrams of uranium 238. From there, it's pretty much the same as what we did before. Use the half-life equation to find the rate constant. Then go to the integrated rate equation. We have our original amount, 6.05 milligrams. We have our ending amount, 4.64 milligrams. And then we're trying to find T. And so we get 1.70 times 10 to the 9th years. So the or is about 1.7 billion years old. So again, a little different in that we're given the mass of the ending material, and we need to work our way backwards to find the mass of the starting material, knowing that the lead 206 came from uranium 238, and applying a mass ratio of those two isotopes to get that starting amount. All right, 967, number 76. Go ahead and pause the video, set that up now, please. I feel like there's a pattern here, so once again, find the rate constants, apply our integrated rate equation. Notice what I did here. Those numbers that we were given, the number of uranium atoms and lead atoms, that totals 100 atoms. And so those are the numbers I use. So we started off, if you start off with, say, 100 uranium atoms, how much would you be left with? So of those original 100 atoms, 67.8 are still uranium atoms, and so that's our amount that remains after time t. And solve for t. We get 2.52 times 10 to the 9th, or 2.52 billion years old. All right, that completes this lesson. Thanks for watching.